What's up, everyone? You've probably heard of a covariance matrix, but can you actually code it up? This problem is listed on deepml.com as an easy problem, but in my opinion, it's definitely a medium, since it's actually pretty tricky to implement correctly. So in this video, I'll show you exactly how to solve it in native Python and in Numpy, and I'll give you some of my pro tips on how to avoid some of the most common mistakes with this question and help you ace your next interview or exam. So if you're new to this channel, in this series, I show you how to solve some key machine learning coding problems, and we're going to use deepml.com here, which is a great website with lots of good coding problems. And as someone with over 6 years of experience in machine learning, I really enjoy solving these. So if you want to get more such content, just subscribe to the channel to stay up to date. Okay, let's dive into the problem. So we're here at deepml.com, and what we're going to do is take problem number 10 over here, which is calculate covariance matrix. So in this problem, we need to write a Python function to calculate the covariance matrix for a given set of vectors, and the function should take in a list of lists where each inner list represents a feature with all its observations. So the observations are going to be all of the same feature, and we're going to see how we're going to play around with them. And we need to return the covariance matrix again as a list of lists and provide test cases to show the correctness. We're actually not going to do that. So in this example, we have this matrix where each list over here, these are observations of the same feature. And what we want to see is how much they vary with respect to themselves and with respect to the other features. And this is actually our covariance matrix. So we can learn a little bit more about this topic. If we look down here, they have a more formal definition of what a covariance matrix is between two sets of features, two observations. What we need to do for this calculation is have the mean of each feature, and then we multiply this normalized version of each feature, also by itself and also with all the other features. And then we get this kind of matrix representation where the diagonal is the variance of a feature with respect to itself, and the off diagonal is the variance of the feature with respect to all other features. So first we need to calculate the mean, and then we need to calculate the covariances. One important thing to note here, and this is one of the most common mistakes, is what we divide by. So as you can see, if we have 3 entries, 3 observations of this feature, we don't divide by 3, we divide by 3 minus 1. That's because we already use up 1 degree of freedom for the mean calculation. So don't make this mistake. We're gonna see it again in the code. Got it? Let's dive in. So we'll close this and we'll start focusing on the code here. So what we want to do is, first of all, let's see how many observations we have and how many features we have. So we'll see how many features we have and how many observations. And we're getting a list of lists. So the number of lists is that's the number of features that we have, and the length of each list, I'm assuming they all have the same length, which they do, but this is the number of observations. So the first thing we're going to do is we're going to calculate the mean. Then afterwards, we're going to calculate the covariance matrix, the covariances, calculate covariances. And that's it. That's actually all we need to do. So these are the 2 steps of the solution. So let's do this in an elegant way. What do you think? Let's use list comprehension. So what we're going to do is sum over the observations of each feature divided by the length of the observations. And what we're going to do is we're going to do this for each feature, because that's what we have in our list of lists. So we can just do this in one line, which is very nice. So this is how we take the mean. So this is the mean of each feature, and each row inside of this vector is going to be the observations of that feature. So this is how we take care of it. Very convenient. Now let's calculate our covariances. So we'll initialize our covariance matrix. So this is we'll initialize it to be all zeros. and it's going to be of size number of features, right, by the number of features. So it's going to have n features rows and n features columns, because we're actually looking at the variances of each feature with respect to every other feature. So that's an n squared matrix. Now what we're going to do is take all the different pairs. So we're going to iterate over all the rows and columns. And there's actually a cool trick here, which I want to share with you, that what we can do is we only calculate the upper half of the matrix, because a covariance matrix is actually symmetric. So if we just calculate the upper half, we can just copy the values to the lower half. And that's how we reduce by half the latency of this. So it's very, very nice. We can save a lot of computation this way. Cool. So what we need to do is first pull out the means of our two features that we're going to evaluate their covariance in this specific part of the for loop. So we'll pull out the mean of feature I and of feature j. And now we're going to do something cool. So what we're going to do, we'll calculate the covariance sum in this following way. So we're going to do this using list comprehension. And what we need to do is take all the observations of feature I, subtract them by the mean of feature I, do the same thing for feature j, and subtract the mean of feature j, and multiply the two. Now, this is exactly how we calculate a covariance matrix. The only thing we need to do here is I need to show you how you can iterate over two things at the same time. So in Python, we have this cool thing called zip. And in zip, this enables you to do just that. You give it two lists and it'll synchronize them, and you can iterate over both of them at the same time. Pretty cool, right? So what we're doing here is we're multiplying the two normalized observations. We're going to sum both of them. And now the actual covariance, don't forget, we need to divide by the number of remaining degrees of freedom here. So even though we have n observations, what we need to do is divide by n observations minus 1. Don't forget that, because we already used 1 degree of freedom for the mean calculation. Now, let's put this into our matrix. So we have the value of the cell ij. And if you remember, the cool thing we did over here is we said, because this matrix is symmetric, we actually don't need to calculate the entry of ji, because they're exactly the same. So we can even make this explicit. So the covariance matrix is symmetric, and this allows us to do this very cool trick. And let's see if we made any mistakes and if we pass all the test cases here. And looks like this runs fine. Very cool. So before we move on to the Numpy solution, let's do a very quick recap. We got the number of features, we got the number of observations, we calculated the means in one whole list comprehension, then we initialized our covariance matrix, and then we're iterating over the upper triangle of the covariance matrix, and we pull out the relevant means for the features I, j. So when we're comparing feature to feature j to calculate their covariance. And then this is the actual formula. And what we're doing here is we're summing over all the observations, multiplying their two variances. And then we need to divide by the number of remaining degrees of freedom, which in this case is the number of observations. One thing that you might want to do is you might want to add maybe another epsilon over here to make sure you don't divide by 0. But that should, you don't have to do that. That should work just fine. Very cool, and don't remember that this is symmetric, so you can save a lot of work. All right, off to the Numpy solution. So for Numpy, we can do things much, much simpler. So we'll import Numpy as NP, and now we can do it in just one line. It's pretty crazy. Covariance is equal to numpy.cov. So this is how we do covariance matrix, and that's it. Pretty crazy, right? So let's convert it to a list and we'll run it. Very nice. It all passes and we're good to go. So remember, there are 4 key things that you need to remember here. To calculate the covariance matrix, you need to calculate the mean, calculate each cell value, fill up the matrix in a symmetric pattern, and don't remember to divide by the remaining degrees of freedom, which is the number of observations minus 1. So there are many more problems over here, and if you want to see some more videos, make sure to check out this next one.